Okay, I would like to welcome everybody to the class. Basically, as many of you, you're highly welcome. So let's get into it. Yesterday we discussed IUPAC nomenclature majorly. We talked about the functional groups and homologous series, as well as the order of priority. In today's class, we are going to start with discussing the IUPAC nomenclature of aromatics. Then from there, we'll delve into structures, and then get into isomerism. See how much you can cover for today. Having said that, we'll get into it. As you can see on the screen, we'll be considering the different rules to identify and name aromatics. But before that, let me just quickly say that aromatics, basically, as we described initially, are benzene related compounds. So once you see a compound that possesses the benzene ring, automatically you are considering this as an aromatic. So you have this. So once you have this, automatically you are considering this as an aromatic. So compounds that have this benzene ring are what we refer to as aromatic. So let's get into it. What are the rules that are applied to name aromatics? The first rule that is applied, as we can see, is to identify the major functional groups attached to the benzene ring. Jointly, they represent the parent chain. So, what does this statement actually mean? Benzene is the main compound. However, when some functional groups are attached to benzene, it automatically changes the name. And we are going to be considering some important functional groups that could change the name of benzene. So let's go to our screen. So imagine you have a benzene ring structure, and with this benzene ring structure, you have that the functional group OH is attached to it. Automatically, this turns this particular benzene ring structure to phenol. So the question is, phenol, how did the name come about? Anytime benzene is occurring as a substituent to another substance, it is referred to as phenyl. So once you want to represent benzene as a substituent to another substance, it is what we refer to it as is phenyl. Generally speaking, when aromatics occur as substituent, they are referred to as aryls. They are referred to as aryls. But when you are specifically talking about benzene, benzene occurring as a substituent is referred to as phenyl. So phenol was gotten from phenyl, which is the benzene substituent, and then the hydroxyl group, which is alcohol. No, not that. Alcohol. So putting these two together, you have that it is going to be phenyl alcohol, and that is what eventually led us to phenol. So my point about it is, once you see the hydroxyl group attached to a benzene ring, it is what we refer to as, excuse me.
Hello, sir.
Yes.
So we can't see it. No.
Oh wow, sorry about that. Yeah. Okay, sorry, I forgot to Okay, thanks. Okay, sorry, I forgot to remove it. My bad, it's my error. Okay, so let's continue. Basically, now, as I was saying, let me just be sure. Yeah. Okay, so let's refresh that. So taking it afresh again, we have that if you consider a benzene ring, and that benzene ring is attached to the hydroxyl group, what we refer to this thing as is phenol. And I said that this is phenol. Why is this phenol? The name phenol came from two things. Whenever benzene is occurring as a substituent, you refer to benzene as phenyl. Anytime benzene is attached to something, it is in most cases referred to as phenyl. That is to say, if you want to use benzene as a prefix, that's the implication. Once you want to use the name benzene as a prefix, you don't say benzene, you say phenyl. When it is going to serve as a suffix or the ending part of the name, you could just use it as benzene or any other thing. But once you are using it as a prefix or as a substituent, it is referred to as phenyl. I now said that generally speaking, when aromatics occur as substituents to any chain, they are referred to as the aryl group. So just have that in mind. You could see the arenes. The arenes are your aromatics, but when they occur as substituents, they are referred to as the aryl. So back to this. I now told you that phenol, the name phenol is gotten from the phenyl group, which is the benzene substituent, and OH, which is alcohol. So if you put these two together, what you are going to have is phenyl alcohol. And instead of calling it phenyl alcohol, we now refer to it as phenol, basically. So whenever you see the benzene ring attached to OH, what should come to your mind is phenol. We'll get to that. So I'm just trying to highlight the different functional groups and how they affect the name of the benzene. The next one I'm going to talk about is when you have a methyl group attached to benzene ring. Now, when you have a methyl group attached to benzene, it is simply referred to as your toluene. Basically, this is your toluene. This is your toluene, basically. You could have scenarios where you have multiple methyl groups occurring on the chain. Okay, for instance, in a case where it's now a dimethyl is what we refer to as a xylene. Dimethyl is what we refer to as a xylene. Now, it is important you take note of these names because they are going to be used in naming. So, a dimethyl is going to be referred to as xylene. There are many forms of xylene. We are going to discuss that as we go further. So just have that in mind. So when the methyl group, one methyl group is attached to benzene, is toluene. When two methyl groups are attached, is xylene. These are the important ones you need to know. Now, the next name I'm going to talk about is when a benzene group is attached to a carboxylic group. A carboxylic group is C double bond OH or COOH. You could have it like this, and then you have COOH. In this case, this is what we refer to as your benzoic acid. So just have that in mind, that once you have your carboxylic group attached to benzene, you now refer to it as your benzoic acid. So this name now is not going to be benzene, it's now benzoic. This is not benzene, this is xylene, because you have two methyl groups, and this is not just benzene, this is toluene. If we are to name this, we'll get to the part of the naming, but I'm just highlighting the important parent chains or parent names that you need to know. Okay, now having said that, I think I'll just mention one final one which is very popular, and we just move ahead. Okay, two more. Now, if an amine group is attached to a benzene ring, it is referred to as the aniline. So whenever you see an amine group attached to benzene, this is the aniline. We will also consider the structure of paracetamol and how paracetamol is related to this structure. Paracetamol is the IUPAC name is para-acetylaminophenol, which means that one of the major things you are going to notice in paracetamol is that it has a phenol group. What does a phenol group mean? You have OH. So just have that in mind. We'll discuss that as we go further in the class. So, but this particular guy, when the amine group is attached to the benzene, is what we refer to as the aniline. And then finally, before I go further in the study, the last one is when you have the carbonyl group attached to the benzene ring, and then you have the benzaldehyde or the benzene aldehyde. So the benzene aldehyde. So this is what we refer to as the benzene aldehyde. So I'm just going to give you guys like 30 seconds to just put this down in your notes, basically, and I hope it is understood. Is there any question so far based on what I have discussed? Okay, any questions so far? If no question, just take some minutes and then put this together so that we would have to continue. Okay, so I presume at this point that we are done with whatever we are putting down, so I have to continue now. So let's go back to that particular rule. Referring to the first rule. Okay, so the first rule says identify the major functional group attached to the benzene ring. Jointly they represent the parent chain. So just have that in mind. Now the note there says the order of priority is considered if multiple functional groups occur in the benzene ring. The functional group of highest priority determines the parent's name. Okay, so see what I mean. Imagine, for instance, you have a scenario. Imagine you have a scenario. Let's say I have this. I have a benzene ring, and then I have OH here, and then I have C double bond OH. So what this rule is simply trying to say is that when you have multiple functional groups, the name of this benzene ring will now be determined by the functional group of highest priority. And if you remember what we discussed yesterday, alkanoic acid is the okapatamata of them all. After your noic acid, alkanoic, you can consider your acid anhydrides, then you consider your esters before we talk about our amide group, then the nitrile, and after the nitrile we went into the aldehydes, the ketones, then we talked about alcohol before amine, and then I think we went into alkynes, alkenes, then the halides, and then you have alkane. In between here you also have your alkoxides, but these are the major ones. Now between alcohol, OH, and carboxylic group, you will notice that the alkanoic acid is far above alcohol, which means that we are going to consider this benzene parent name with respect to the carboxylic group. Why? It is the functional group of highest priority. So instead of calling this a phenol, I am going to call this a benzoic acid, which means automatically the OH will now serve as a substituent. So just have that in mind, that that's basically how it works. Okay, imagine, for instance, let's say you have this. Let's say you have okay, imagine you have CH3 and then you have OH. So what do we think this is going to be? Is this going to be toluene or phenol? Put out your answers quickly. Is this going to be toluene or phenol? Put out your answers quickly. Is this going to be toluene or phenol? Yes, let's have it. Okay. Yeah, what's it going to be? One answer and I just continue. Is it going to be toluene or phenol? Exactly. It's going to be phenol. Why is it going to be a phenol? Because the alkyl group definitely is below. Okay, yeah, Praise said toluene. Now let me explain. If you look at the order of priority, let's go back to my board. In the order of priority, this is where alcohol is. The alkyl groups are substituents. They are not even in this order of priority, which means they are the last things considered. Alkane is the last thing that you consider. You could consider alkyl below here. Alcohol is higher than the alkyl. which means I'm going to preferably consider this in relation to OH than in relation to CH3. Praise, is this clear? Praise, is this clear? Respond if you got this. Is it clear, Praise? Ooh. Oh yeah. Oh. Okay. I'm still waiting for a response though. Okay. So it's supposed to be, I don't think I can wait. Okay, yes, good. So let's continue. Sorry, I had a little glitch in this thing. Okay, let's try one more just to be clear that everybody understood what I just said. Now, remember, oh, I cleaned it. Okay, let me put the order again. Alkanoic. Then you have your anhydride, your acid anhydride, your ester, your amide, your nitrile, your aldehyde, your ketone, your alcohol, the amine, your alkyne, alkene, halide, alkane, or alkyl, basically. Okay, so yeah, let's come back. Now, imagine I have this structure and I give you a benzene ring where I have C double bond OH, and then I have OH. So is this going to be a benzenaldehyde or a phenol? Quickly answer the question. Is this going to be a benzenaldehyde or phenol? Is this going to be a benzenaldehyde or phenol? Let's do that quickly. One answer and I just continue. I just want to confirm that we are all following before I move ahead with the others, because this is one of the most important parts. Understanding how these things work would help us so much in our study. So yes, quickly, one answer and I continue. It seems there's a little bit lag between my time and you guys, basically. Exactly. So it's supposed to be a benzenaldehyde. Why is it supposed to be a benzenaldehyde? Because in the order of priority, benzenaldehyde, the aldehyde is higher than the alcohol. So automatically you refer to this as a benzenaldehyde. Okay, let's continue. Having said that, we'll move ahead to the next rule. Okay, yeah, correct. Now, with that said, let's look into the next rule of the study. The next rule now says, allocate locants to the carbon atoms of the benzene ring, starting from the functional group of highest priority. What does this simply mean? It means that the carbon atom of the benzene ring will be allocated some numbers, and those numbers are going to start from the carbonyl group, the functional group of highest priority. Okay, so what does that mean? It means that if I'm going to give numbers, the person that will have this is carbon, we might not understand or know this, but let's have that in mind that you have carbon atoms in this benzene ring. Note, they did not say you should allocate locants to the carbon of the functional group. The locant you are allocating is to the carbon atoms of the benzene ring. So, which means that if I'm to give a number, this particular carbon that has the highest functional group will have the number 1. If I draw another structure, for instance, I have this. Don't mind my horrible structure. And then here I have COOH. And then here I have OH. If I'm going to start numbering, I am going to start numbering from here. This is my number 1. So just have that in mind, that the carbon atom attached to the highest functional group or the functional group of highest priority is where you are going to start numbering from. So let's see the other rule and understand how we now continue numbering, basically. Okay, so but before I continue, hope this was understood. Hope this is clear. Hope this is clear. Please respond, just one response, and then I move ahead. one response and I move ahead. Okay. Yeah, okay, so let's continue. Now, moving ahead, we go to the very next principle. Now, the next rule says, after we finish allocating, so they now said, note, allocate the numbers such that the other substituents will have the smallest possible number. So let's apply that principle now. They said when we are allocating this locant, allocate it so that the other guys will have the smallest possible number. And how do we do that? That's the question. How do we do that? Let's look at the board. Now, let's start with this guy. If we are to allocate numbers, we already agree that this is number 1. We can either go clockwise or anti-clockwise. If we decide to go clockwise and number, we are going to have that this is going to be 1, this is 2, this is 3, this is 4, this is 5, and this is 6. Notice something. The hydroxyl group in this case has carbon 6. Now, if we decide to number anti-clockwise, the numbers will change. So let's do that anti-clockwise. If we are numbering anti-clockwise, we would have this as 1. This is now going to be 2. This is going to be 3. This is going to be 4. This is 5, and this is 6. So notice this, that if you had numbered clockwise, you will find out that the hydroxyl group will be on carbon 6. But because we numbered anti-clockwise, automatically the substituent now has carbon 2. So when you are giving your numbers, make sure you are starting from the side and going towards the direction where the substituents are closer to the first carbon atom of that benzene ring. Okay, so if we are to number this now, this will be 1, 2, 3, 4, 5, and 6, which means hydroxyl is on carbon 3. If we had numbered anti-clockwise, we are going to have 1, 2, 3, 4, 5, 6. Notice that the carbon of the hydroxyl would have it can either be 3 or 5. But because we know that the substituents are supposed to possess the smallest possible numbers as their locants, the implication is that we are going to number in this direction. Okay, so just to help us understand this, you guys are going to identify the number of this particular substituent for me. Imagine, for instance, I have yes, let's use a benzoic acid, and then take, for instance, I have let's say I have something like the amine group. Okay, so can you please tell me the number of the amine, that is the locant of this amine attached, or whichever one is the substituent? What's the locant of the amine? Quickly put out your answer. What is the locant of the amine? If it is 1, you tell me it's 1. If it's 2, you tell me it's 2. If it is 3, you tell me it's 3. Basically, what is the locant of the amine? Okay, quickly, let's do that. There's no time. I want to talk about structures today and possibly get into isomerism. What is the locant of the amine? What is the locant of the amine? Exactly, it is 3. Why? We have to number in such a way that it's going to be closer and you to give the lowest possible locant. So that's going to be, if we number, I presume you numbered this time around clockwise, which is 1, 2, 3, 4, 5, 6, basically. Okay, so we go to the final rule and then call it off there. Okay, what's the final rule? Now, the final rule states that the substituents and their locants are attached to the parent names as prefixes. So just as we discussed in the last class, just pack them and attach them to the parent name as prefixes. Remember that if there are multiple or many of them, you just simply you utilize the alphabetical order in your arrangement of the prefixes. We did this yesterday. So let's explain this with a structure. Let's now name this structure we have on the screen. And if I want to name this structure, I already know that this is a benzoic acid because it is the functional group of highest priority. So the parent's name is going to be benzoic acid. Now, if I now have an attachment of, this is an amine group, you get, and because the amine is not higher than the benzoic, is going to occur as a substituent. So to name this thing, it is now going to be amine. But where is this amine? Amine benzoic acid. But where is the amine attached to? It is attached to the third carbon. So this is going to be 3-amine or amino benzoic acid. So the name of this compound is going to be 3-amino benzoic acid. So please notice something, that I had a hyphen between a number and the letter, and then there is no spacing between letters basically. So that's basically how to name this your arenes or your arenes basically. Okay, I hope this is clear. Okay, let's try one or two more. Okay, so you guys should try this one now. Imagine I had something like this. I had something like this. Let's say I have OH here, and then I have okay, so let's try naming this one. Let me include one more. Okay, so what do we think is going to be the name of this particular compound? Yes, what's the name of this compound? Let's do that quickly. Put out the name, put out your suggestions quickly. Put out your suggestions quickly. Okay. Let's be fast about this. Okay. Okay, I think I've seen this. Oh, sorry. I wasn't here. Did 1,4, is that 3,4 diaminophenol? 3,4. Okay, yes, sorry. Anyako, I did not get what you did that there initially. Okay, so let's look at the screen. So we have 3,4-dichlorophenol. Anyako said, yeah. Okay, so we are correct, basically. So that's that basically. So let's look at this structure. Now, and if you notice this particular structure, we all agree that it is a phenol, basically. And this phenol, we are going to be counting from one side. If you count from here, you are going to have 1, 2, 3, 4, 5, which means you have 4 and 5. That is counting clockwise. But when you count anti-clockwise, it's going to be 1, 2, 3, and 4. 3 and 4, which means automatically you should count anti-clockwise. So this is going to be 1, 2, 3, 4, 5, and 6. So this is phenol as the parent name. The chlorine is now going to be 3,4-dichlorophenol. And that's correct. Okay, let's try one more. I probably have not mentioned this, but when you talk about your dioic acid, the dioic acid is what we refer to as the phthalic acid, basically. So if it is, once you see that the carboxylic group is 2, you have 2 carboxylic groups, one here and another on the second carbon atom or adjacent carbon atom. What we refer to this as is phthalic acid. So please put this down, basically. Now, if you have a scenario where they are now parallel to each other, the carboxylic groups are now parallel to each other, it's no more referred to as just the phthalic. It is now referred to as the terephthalic acid. So please just put this down quickly, basically, and just take note of that. Okay. With that said, let's name this. What would this now become? Imagine you have NH2 here, and you also have NH2 here. So let's name this particular compound. So as I said, once you have the carboxylic group on 1,4 parallel to each other, is now terephthalic. But if they are adjacent to each other, it's just referred to as the phthalic acid, basically. Okay, so let's name this one to show how much you understand this quickly. Let's do that quickly. Just this one, the A. Name A. Name A quickly. Okay, so let's do that quickly. Okay. Okay. Okay, so that's going to be 3,4 diaminophthalic acid. Yes, correct. Both of you are correct. So let's continue. Now, having said this, we are going to, I initially mentioned some other compounds. I'm just going to put out the examples for you guys to like possibly answer. Let me just put it out so that we'll be sure that this is clear. And now you also notice something too, that when you are going to be allocating this number, you are starting from the side that has most of the functional group and most of the substituents. That's one point that I want you to take note of. Now, before I give you the examples to solve, I would like to quickly talk about another system of naming, and it's more like an older system of naming. That is what I refer to as the UMP. When I say the UMP, I mean the auto, the meta, and the para. So it is characteristic to your benzene ring compounds, basically. The reason some of you might not be able to identify or draw the structure of paracetamol is simply because you don't know this thing. Now listen, when you consider the auto, meta, and para, auto simply means adjacent to. So once you are looking at the particular carbon atom that is adjacent to the main carbon atom which carries the functional group, let's use this for instance. If I have OH here, automatically this is number 1 carbon atom. So when I say auto, the implication is that I have that the carbon atom that is auto to this guy is this particular one or this particular one. So just have that in mind, that auto simply means adjacent to the main carbon atom. The main carbon atom is the carbon atom that carries the functional group. So when I say auto, it is adjacent to. And auto is more like a 1-2 arrangement. So when you have 1-2 from this side or 1-2 from this side, automatically you are referring to this as an auto arrangement. Let's apply this to a name. Imagine, for instance, I have this particular compound, phenol, and I have chlorine attached to it. The name of this compound is going to be 2-chlorophenol. But if I want to use the UMP naming system, I'm going to refer to this as orthochlorophenol, basically. So do I have any questions? Is there any question? I hope this is understood. Hope this is clear. Yes, just one answer and I continue. Hope this is clear. Just one answer and I continue. Yes, one answer and I continue. I need to continue class. There's no time. Hope this is clear. Okay, no questions. Moving ahead. Okay, so that's that basically. Now we go to the next one. The next one is meta. When you talk about meta, meta is more like a minor group. Most compounds do not have the arrangements in the meta state, and meta is more like the 1,3 arrangement. So if this is your main carbon atom, your meta would now be here. So this is meta, this is 3 now. This could also be 3 from the anti-clockwise direction. This is also meta. So just have that in mind, that when you talk about your arrangements with respect to the other groups using the system, 1, 2 represents auto. 1, 3, if it is on the third with respect to the main carbon, it is now a meta group. And I said that the meta is usually a minor, which means most of the compounds you are going to have, instead of having 1, 3, you would either have 1, 2 or 1, 4. Meta states rarely occurs. That is to say, where you have a 1, 3 arrangement. So just have that in mind. So it's after the adjacent carbon you have the meta, and as I said, it is a minor group. Now remember that this auto is supposed to be a locant. So if we are to put this name together, it should be separated from this by a hyphen. I'm just saying so that you will know. In most cases, they just put O-chlorophenol. If I have another structure, something like this, and then I have OH here, and then I have chloro, this is going to now be M-chlorophenol or 3-chlorophenol. Basically, that's that about the system. Then we come to the final one, para. You can literally understand this one. Para means parallel. So parallel to the main carbon atom, and that's a 1, 4 arrangement. So what is that going to indicate? That here is going to be the para, which means if, for instance, I have a diagram, and in my diagram I have this as OH, and then I have this as chlorine, the name of this compound is going to be 4-chlorophenol. 4-chlorophenol. If I don't call it 4-chlorophenol, I'll call it parachlorophenol. Parachlorophenol. If I don't use the parachlorophenol, I'll now refer to it as p-chlorophenol. So that's that basically. So these are the 3 major ways of understanding the names of these compounds. To help you understand this, I would like you guys to use the system to name this, just to check if you understood what I just said. So name this compound. If, for instance, I had something like this, okay, so I have chlorine here, and this is going to be, so let's name this compound quickly. Let's name this compound quickly. Let's name the compound quickly. Let's name the compound quickly so we can move ahead. There is no time. We still have to talk about the different types of structures, converting structures to names to structures, and then get into isomerism possibly. Oh yeah. Oh. So let's name this quickly. One of the reasons I'm taking my time to do this is so that I'll be sure that I covered every angle, and somehow with this study you can practically be able to name most of the organic compounds that you're going to see in 100 level. Basically, that's the aim of this class. Okay, so quickly, yes, one answer and I move ahead. One answer and I move ahead. Exactly, that's going to be the M. Check it again. Omenazu praise, you forgot to indicate the name of the substituent. You forgot your chlorine, so I think you should try that again. Try that again. Chloro they there now. You're not just saying M-benzenaldehyde. You are going, the M is representing the substituent there. So what is the name of the substituent? You omitted it. Okay, hope that is understood. So let me see your correction. Let me see your correction to that so that I can continue. Presume you can hear me. Okay. If you don't understand, you can indicate that you don't understand. Just type you don't understand and I would. Okay, let me just answer this one and then probably give you guys another. Now, as you know, this is 1. We will count anti-clockwise 2 and 3. Remember, this is going to be, this is auto, this is meta, and this is para, basically. So just have that in mind, that 1, 2 is auto, 1, 3 is meta, 1, 4 is para. So if we are naming, the first name for this compound is going to be 3 chloro benzenaldehyde. Okay, that's the first name. The other name we can call it is metachloro benzenaldehyde. And then finally, if we are just, you know why it's meta? It's adjacent to the adjacent carbon to the main. Yeah, so basically, so that's going to be M chloro benzenaldehyde. So any of these 3 names you put there is going to be the correct one. Okay, yeah, makes sense. Yeah, basically. Okay, having said this, I would now have to go to, let's try one or 2 more examples basically to help buttress our points. Then I'll show you the structure of paracetamol and then we would move ahead. Okay, so imagine you had this. Imagine you had this structure. Let's see. Okay. 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 Yeah. Okay. So try naming this compound. What do you think it's going to be? Okay. Let me even make it more complicated. Yes. Oh yeah. So try. What do you think this compound is going to be referred to as? What is this going to be referred to as? Let's do that quickly. Okay. So what's the name of the compound? Yes, just one answer and I move ahead. One answer and I move ahead. What do you think? Quickly and we move ahead. Gang. Okay, still waiting for that answer. I think there's a little lag with respect to. Okay, so you have 2,3,5 trichlorophenol. Good. Now I want you to name it with respect to the UMP naming system. What do you think is going to be? The UMP. Okay. If you use the UMP, the implication is that. Okay, I see what you did there. Now, the implication is, you know, there is nothing for 5, basically. There's nothing for 5, so the UMP naming system might not work here. So yes, but 2,3,5 is actually correct. MMN trimethyl. Let's see. This is M. Nah. This is supposed to be auto. O. Okay, so let's go back to the screen. So if we are going to name this, let's name it with the numbering system. This is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. Why did we say that this is 1? Because this is the functional group of highest priority. So you start counting from the functional group of highest priority. So with that said, we've allocated locants. So this is going to be phenol. Now, knowing that this is phenol, the next thing we are going to do is we are going to count, and you notice that I counted anti-clockwise because the substituent is closer. So this is going to be 2,3,5 trimethyl. This is ortho. This is meta. This is para. Basically, this guy, you just put the number. So we could say that this is going to be O, M, 5 trichloro, sorry, not trichloro, trimethylphenol. Trimethylphenol. That is if you are using the ohm system, but normally it should now be 2, 3, 5 trimethylphenol. Okay, so that's that basically. Now, I mentioned paracetamol, and as I said, the IUPAC name for paracetamol is basically para-acetyl aminophenol. Okay, so let's break this down. As you notice, because you are seeing phenol as the suffix, it implies that the phenol here is the functional group of highest priority. So let's indicate the phenol. The next question is to understand what an acetylamine is. The acetylamine is when the acetyl group is attached to an amine group. If you have the amine group, which is nitrogen, before we fill the hydrogen, there's supposed to be 3. You have that this amine attached to an acetyl group. The acetyl group is actually produced from your acetic acid. Your acetic acid is COOH. That is your ethanoic acid. You get. So if you remove this OH from here and replace it with something, this particular group is now referred to as the acetyl group. So have that in mind. If I'm going to attach the acetyl group, because it's acetyl amino, let's put that together. Acetyl amino. So this is going to be CH3C double bond O. Oh, sorry, not that. The replacement is actually, yeah, OH is replaced here. So you have C double bond O, and then you have CH3, basically. So this is the joining. Now, one of the bonds in nitrogen will have to be attached to the phenol group, while the remaining one is for hydrogen. So if we attach this whole thing here, remember it said para. So the positioning is going to be parallel to the functional group. If it had said ortho, it would be here. If it had said meta, it would be here. But because it said para-acetylamino, automatically you are going to have the acetylamine attached at this point. Hydrogen here, and then we have your acetyl group, which is Ca and then CH3. So this is what we refer to. This is basically the structure of paracetamol. What we refer to this as is the para-acetyl aminophenol. The acetylamine is this guy here. Acetylamine. And I now mentioned that the acetyl group is formed when you remove the hydroxyl group and you have something like CH3 from the acetic acid. The acetic acid is your ethanoic acid, basically. So you have that. I hope this structure was understood. Okay. Yeah, MMO. I have corrected this basically. I told you guys the implication of, you can't have that for 5. The number is already 5, so you can't say 3. It's not 3 3. You get, it's M is for 3, then indicate 5 because 5 does not have a special name. I presume this is understood, so I will have to move ahead for want of time. As I said, or as I do say, hope this is clear. Now let's leave that and get into other things that we have for today. So basically, this is the basic principle or the principles behind naming your array groups. Let me just put out this. You guys can try this out later. Let me see if I have them. I think I'm going to have to put that out in the group later, and I'll put that out in the group study group later for you guys to look through. No, this was not, I think it was the aniline. Where? Yeah, aniline group. Okay, so if you could actually look this up later and then look into these different structures and find their IUPAC names. These are their trivial names, but it's important you you find their IUPAC names basically. Yeah, okay. Okay, so with that said, yeah, Dubemeze, you are just joining the class, we don't go far. However, you can review the video later. What I'm going to do is that I am going to we are getting into a new part of the study. We don't finish the first part, so we don't talk about, so we are getting into the new part. So later, go and review the study. So as I said, you guys should look into these structures and possibly generate their IUPAC names, having in mind that these are their trivial names. We'll talk about them in the group later. Okay, now having said this, I would take this out quickly. I said I'll send it later to the group, so just in case you are confused about that, you will get it later in the group. Okay, where is it? Where's my real group? Okay, so let's continue with what we were discussing. The next aspect of today's study is going to be organic structures. Basically, we are going to discuss organic structures and then see how to generate these things. Now, there are 5 major forms of organic structures you get. We'll start with the first one, which is the common structure. Now, the common structure basically represents carbon and the bonds to different atoms. The implication is that when you are putting out a common structure, you simply put out the carbon atoms. Bear in mind, carbon forms 4 bonds and attach the atoms individually. If there was chlorine here, you attach it, just attach it individually. This is basically what we refer to as the common structure. So in common structures, the carbon atoms, okay, let's just use hydrogen for now. We'll discuss these other ones. So in the common structure, what you have is that the carbon atoms are outlined and the individual atoms are attached in singly to these carbon atoms. That is basically what represents the common structure. Now, the next structure I'm going to talk about is the staggered structure. One of the reasons I'm talking about this is because I'm going to get into the other aspect, which is converting names to structures. So we need to understand the different structures that exist. The staggered structure is simply formed by putting out or putting together these atoms. All these atoms that are attached to carbon, just put them together. For instance, here I have C and H. There are 3 of them. So I'm going to call this CH3 instead. This is now going to be CH2 instead. This 2 is going to be CH2 and this is CH3. And this is what we refer to as the staggered structure. Notice that the carbon atoms is still 4 and the number of hydrogen is still 10. Same thing here. So they are just different ways of representing the organic structure. So this is the common structure, which has everything singly separated. Then the staggered has atoms that are surrounding carbon atoms that just put together, basically. Then that's that about the staggered structure. We go to the next one, which is the zigzag structure. The zigzag structure is just like the name, zigzag. So carbon to carbon, carbon to carbon. You see, I just bent the direction. You know, I could just put it here, put here, put here. Once you are just bending it in different directions, what we refer to this as is the zigzag structure. There's nothing much about that. So the zigzag structure basically has the carbon chain not in a straight line but in a zigzag form. So filling it, there are 3 hydrogen atoms here, there are 2 here, there are 2 here, there are 2 here. I can decide to write it like the common structure. Fill the hydrogen. Okay, let me zigzag first. Here I now have 2 hydrogen atoms. Here I have 2. Here I have 3. This is what we refer to as the zigzag structure. So I take it again. This is the common structure, straight line. Everybody is attached individually or singly to the carbon atom. Staggered structure. The carbon atoms are aligned, and after they are aligned, the atoms that surround them are put together and written in front of each of these carbon atoms, basically. And this is the staggered structure. Then the zigzag structure is just as the term, zigzag. And you have that basically as the third type of structure. I presume this is understood. Any questions so far? Any question so far? Any question? Any question? Just one response is what I need. I'll move ahead. There's no time. I just want to be sure that we are following while in class. That's all I'm doing. Yes. Do I have any questions so far so I can move ahead? No question. Very good. Now, that is what we refer to as the zigzag structure. We go to the next structure. The next structure we are going to talk about, I'm going to remove this whole thing. I presume, okay, just take 30 seconds to put this down quickly. If you haven't done that, just quickly put this down. Yeah, just do that quickly. Okay, I presume you're done with that. We'll go to the next structure. The next structure we are going to consider is the condensed structure. Now, the condensed structure is quite simple. First of all is that, let me just put down my staggered structure on the side so that it will help me draw a condensed structure. The principle behind the condensed structure is once you notice common things in the chain, put them together and write out the multiple that would give them. For instance, did you notice that in this chain you have CH3 here and you have a CH3 at the end? Now the terminal carbon atoms are usually left as they are, usually in most cases. However, the rest of them can actually be put together. Now CH2 is here, you have another CH2 here. What you can simply do is put them together. You call it CH2 all multiplied by 2. That's the staggered structure. So here I'll now have CH2 into how many places? 2 places, and then end it with CH3. This is what we refer to as the condensed structure. This is staggered. But when you put together common things in the staggered structure, what you have is a condensed structure. Now, once you notice that it is CH2, just know that that is supposed to be part of the chain. If you see CH2, it is supposed to be part of the chain. Have that in mind. Once you see CH2, it is part of the long chain or the continuous parent chain. It is not a substituent. Now, however, you could have scenarios where you have alkyl groups attached. You could have anything attached, and that is what I'm going to explain. Now, so talking about that, imagine for instance, let's try a different example. If you have this as your staggered structure, staggered. So let's say this is your staggered structure, CH3, CH2, okay, no, let me not use CH2. Let's say I have CH3, I have another CH3 here, I have another CH3 here, and then I have CH2, I have CH2, and then probably have C, H, and I have CH3, and I have C, H3, CH, CH3, and then another CH3. This is basically the staggered structure. If I want to convert it to a condensed structure, what am I going to do? I will look out for common things and put them together. CH3, CH3, CH3. Now, they are 3 of them are attached to this carbon atom. So what am I going to do? I'll put a carbon atom and then put the whole CH3. I notice that there are 3 CH3 surrounding this carbon. So this is going to be CH3 into 3 places. Then I continue. There is CH2 and CH2. Because they are common, I'll put them together. Remember, once you have CH2, it is part of the length of the chain. This is going to be CH2 into 2 places. And then I have C, which is attached to hydrogen and CH3. I could just put CH and then put the bracket CH3, basically, and then move on to this one. I have 2 CH3 surrounding this carbon atom and 1 hydrogen. So this is going to be CH bracket CH3 into 2. This is the condensed structure. So it seems confusing at first, but what we're going to do is we're going to keep trying out ways of getting this condensed structure or expanding the condensed structure. As we try it out, I presume we'll get used to them. But this is how to deal with the condensed structure. Okay, so far, do I have any question before I continue? Okay, any Okay, you have, but no worries. If your network is that horrible and you can't join the class live, the study is there. You can look it through later. You get. But I would actually appreciate it if you can try as much as possible to join the class live, because I will get to answer your questions directly. So yes, before I continue, any question for those of us that still have service? Any question? No questions. Very good. Okay, so let's continue. Now, having said that, we will try out other structures. Let's try out other structures. Let's see. Imagine, for instance, now I would show you how to convert a condensed structure to a staggered structure. There are principles that you should follow when you are doing that. Imagine I have this condensed structure, C bracket CH3 into 3. I have CH2 into 4. I have C bracket CH3 into 2. I have CH2 into 2. Then I have C bracket CH and then CH3 into 2. Now we're going to expand this thing together. The principle behind expanding is, once you count a carbon, anything in front of that carbon atom will surround the carbon atom before you continue moving ahead. Then the second principle you need to note is that CH2 is part of the length of the chain. It is not a substituent. But if you have any other thing that is not CH2 attached to a carbon, then most likely it is a substituent. So you need to surround it first before you continue. Okay, so let's put this down together. Imagine I want to expand this. What am I going to do? I start with this. I draw my carbon atom, and then I have CH3 into 3 places. So that means I'm going to put CH3 on one side, CH3 on the other side, and CH3 on the third side. Notice that I did not put it in front intentionally. So let's continue. Now we move ahead. Because this is CH2, I know that it's part of the chain. So I have CH2, 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 CH2. This is part of the chain. Why? Because it's CH2. Once it's CH2, just know that it's part of the chain, basically. And there are 4 of them. Moving ahead, I now have yes, I have C, and yeah, this C. We are now here. So you put down the C. You notice that you have methyl groups, 2 methyl groups in front of these guys. So you put it as substituents around it, not in front. CH3. And then I continue. I have CH2 again in 2 places. And then finally come to this carbon. Now in this place, I have 1 hydrogen. And then I have CH3 in front. And then have another CH3. And that's that basically. So this is the actual structure of this compound. Now, why did I have to show you this particular system? The simple reason is this. Anytime you have a condensed structure and you are asked to name, the wisest thing to do is to expand that particular structure before you start naming. The simple reason is, if you leave it condensed, you could get confused and then give it the wrong name. But once you expand it, especially those of you that are just learning how to name, it's easier. In fact, as much as I know so much about naming, I still have to expand before I name. So the wisest thing to do is, once you have a condensed structure, expand it and then you name. So together we are going to be naming this compound, and once we are done naming it, I'll give you an example that you guys are going to help me name. So let's put that together. So if we are to name this, first of all is you will notice that if we are to the both ends have close carbon atom, but I think there are more substituents. There are more substituents closer to this place, because if we count, this is 1, 2, 3. That is 1, 2, 3, 4, 5, which is going to be 255. But here 255 255 this. Okay, let's look. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so this is going to be 255 10 10. 255 10 10. 2, 5, 5, 10 10. Okay, so let's check from here. This is going to be 2 2 2, 2 this is not going to be 1 2 3 4 5 1 2 3 4 5 6 7 2 comma 2 7 7 7 7 10. Now what we're going to do is we are going to add these numbers and see which one is lower, basically. So this is going to be 2 plus, this is 10 32, we have 32 here, 14 24 24 25 26 28. Okay, so the implication is we're going to take this. Why? The locants would give a lower number with this numbering than this numbering. I'm sorry, is it confusing? I hope this what I just explained is clear. Hope what I just explained is clear. Oh. Hope it's understood. I just explained something. I hope it is understood. I just want to be clear before I move ahead. That is, I'm going to preferably number from this other side. Okay, so moving ahead, we are going to number from here, because when you add the locants, you will notice that this one has a smaller locant than the other. So this is 1 2 3 4 5 6 7 8 9 10 11. Now to name this compound, I prefer to circle out my, I told you guys that that's how I deal with it. I circle out my parent chain, which happens to this one, happens to be this one, before I even continue doing anything. Now let's now name this compound together. Now I have methyl, 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 methyl. Methyl is just the only substituent. So where are the methyls? I have 2 2, these ones, 7 7, and then 10. How many methyls? 1 2 3 4 5. That's going to be penta methyl. That's all about the substance. The parent chain is undecaying, and that's that. Quite easy to understand. So you notice that if you are trying naming it like this, you might not be able to get this. So before you start naming, it is important that you expand the condensed structure. Okay. Okay, now having said that, I will have to move ahead, basically, so that we don't have much time. Now you guys should try this one, just to be sure that we understood what I did. You all should try this one now. Take for instance, I have C, okay, CH3, I have C, H2, let's say I have 5 of this guy, and then I now have C, Br, CH3, and then I have C, Cl2, and I have C, CH brackets C2H5. Then I have C, I have CH brackets CH3, and then finally C brackets CH3 into 3. Okay, let's try naming this compound and see what we come up with. Yeah, let's try this. Let's see what we come up with. Everybody try naming this compound, and then what do we have? Once I have your answer, I shall continue. Okay. Oh yeah. Expand and name. And name the compound. Expand and name the compound. Quickly do that. Expand and name the compound. Expand and name the compound. So I'll give you guys like 1 minute to do that. I'll give you guys like 1 minute to do that. Expand and name the compound so we can be able to push ahead. Expand and name the compound. Quickly do that so we'll continue. Okay. Okay. Oh yeah, oh. Expand our name so we'll continue. No time. Abi, is it unnameable? Okay. Just any answer. Put out any answer you think so that we'll move ahead quickly. We still have isomerism to discuss, so let's be fast about that. Oh yeah, oh. Expand our name. Gang. This one I had pass. Okay. I think I have to come in at this point, basically, for want of time. You can still put out your answers, Sha. But let's cross-check it with mine. Now, remember, we are going to expand it before we start naming. How do we expand? Each carbon atom, whatever is in front, is surrounding the carbon atom. Because this is hydrogen, I don't think I need to like overemphasize or like spread it. We go to the next one. CH2. I told you once you see CH2, it's part of the chain. So there are 5 CH2s. So CH2, 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 and CH2. Basically. Then we come to this. We have another carbon atom. In front of this carbon atom is bromine and methyl. So I need to fill them around first. Bromine and methyl. I can place my bromine here and the methyl here. It doesn't necessarily affect this. Then I go ahead and I notice that in front of this carbon I have 2 chlorines, which means chlorine here and chlorine here. I move ahead and in front of this carbon I have hydrogen. Notice that I'm following this thing in a particular sequence. And then I have the ethyl group. So under I have C2H5. The ethyl group can be on top and hydrogen is below. It doesn't mean anything. Then I move ahead and notice that here I have another carbon. I'm taking it one after the other. In this carbon, I have hydrogen here. And then methyl is surrounding it on the other side, so CH3. And then I continue to the other one, which is the last carbon atom in this chain, which has 3 methyl groups. One here, and one here. And that's that. The very first thing we are going to do is to circle out our parent chain. And if you have been in my naming class, you would notice that this is the parent chain. Like obviously that's the longest chain. Okay, so that's that. Now the next thing we need to do is now to give this a name. Locant is going to start from here. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, which means the parent's name is going to be dodecane because it's all single bonds. Now let's get to put or allocate these things now. Let's write out all the functional group. I can see a methyl group. These two are methyl. This is also methyl. This is an ethyl group. Ethyl, because it has 2 carbon atoms. This is chloro. I notice chloro. I notice methyl and bromo. I don't think there's any other. Arranging it alphabetically, I'm going to start with bromo. After bromo, I get to chloro before I talk about the position of the ethyl, then the methyl. Okay, having said this, let's put the name together. Now, this is now going to be bromo is on number 6. This is 6 bromo. 6 bromo. Hi. 6 bromo. There's only 1 bromo here, so let's just continue. 6 bromo. We go to chloro. Chlorine is on number... Yeah, we have chlorine on number 5. So that's going to be 5, 5 dichloro. That's chlorine. Then we come to ethyl. Ethyl is on number 4. 4-ethyl. 4-ethyl, and that's the only ethyl here. And then we talk about the methyl. Methyl is on number 2, 2, 3, 6. So that's going to be 2, 2, 3, 6. 2, 2, 3, 6. And you have that as tetramethyl. Because that's the last substituent, then we now attach our parent's name, do the K. Okay, most of you are not able to type this, I guess. Okay. Okay, so let's see your attempts and see how many of you were close. Okay. Yeah, bromine is on number 6, not 5 for praise. So that's 6 bromo 5 5. Okay, so I see probably, I hope you've seen the correction now. If you notice, you probably did not start counting from that first carbon. That's why before you start naming, circle out your parent chain so that you'll be seeing your substituents clearly. Because I think what happened with your own naming praise is that you probably started from here. And if you do that, you would consider this as a methyl group, but no, it's part of the parent chain. So let's see. Yeah, you're quite close. 6 bromo 5 5 dichloro. Yeah, 4-ethyl makes sense. 2 2 3 6 tetramethyldodecaine. Yeah. Kachi, you're on it. Makes sense. So Kachi is correct. Praise, you need to like take your correction. But praise, hope it's clear. Praise. Hope it's clear. Praise, talk, make I know. Okay, so let's get to that. Now, that is the... Okay, correction taken. Makes sense. Now let's move ahead. Now, what we talked about is the first structure. And the final structure is the skeletal structure. Now, there are things you need to note about the skeletal structure. The first point to note is that terminals when I say terminal, I mean the ends. Terminals, ends, and junctions indicate carbon atoms. The second point about the skeletal structure is multiple lines indicate multiple bonds. So the skeletal structure is a very weird structure. It's just lines basically. So but the point about the skeletal structure is that every end and every junction indicates a carbon atom. So this is actually an organic compound. This is 1 2 3 4 5 6 7 8 9. So this is nonane. How do I know that this is nonane? The point said terminals and junction. This is a terminal, so this is a carbon atom. This is a junction, so this is a carbon atom. This is another junction, this is a carbon atom. This is another junction, this is a carbon atom. This is a carbon atom. Carbon, carbon, carbon. This is a terminal carbon. So once you see each of these things represent carbon atoms. If we are to name this guy, it's going to be 1 2 3 4 5 6 7 8 9. Because it is all single bonds, it's an alkane, and this is going to be non-ane. And you have that. I hope this is clear. Okay, you guys should try this. Imagine I have this basically. Okay, yeah, this is like madness, but try naming this. What is this going to be? So yes. Oh yeah, let's attempt naming this one. This one looks like madness. Oh yeah, oh. But the basic principle is junctions and terminal points represent carbon atoms. This is quite easy to understand, so please do this. So we'll move into more important things. This is important though, but you know, there are other things we have to discuss. Okay. Just one answer. Okay, now 17. Mo will counter. He said it's 17. Let's check, Sha. I think it's 16, but let's count, Sha. Let's count. I don't even know which I draw there. So this is carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Makes sense, 17. And 17 carbon atoms is what we refer to as heptadeca, which is heptadecane in this case, basically. And that's that. It's quite easy to understand. Now, we are going to like get into different versions of the skeletal structure. So, work with me. Now, you all should try naming this. Imagine you had something like this. And probably you had this and this. I'm going to name this one, and then you guys are going to try naming the other one I'm going to give you. So let's name this compound together. It looks very dumb and looks like jagra the Nigerians, but this actually is a representation of a particular organic compound. So let's get together. So this is going to be, there's one carbon atom here because it's an end. This is a junction, there's a carbon atom here. This is an end, there's a carbon atom here. This is a junction, there's a carbon atom. This is an end, carbon, 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 carbon. This junction here, carbon, 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 carbon. Okay, so we are able to put our carbon atoms. Basically, the next thing to do is to find the parent chain. I can already see it here. I like circling out my parent chain. So basically, this is how my parent chain. Now, if I had gone through this side, it's shorter. So I have to continue basically. Yeah, let's just circulate out like this. So now notice I am following the sequence of single carbon atoms. This is one carbon basically. So you have that. Now, just to avoid the confusion, let me just take it back again. Now I went from here. I'm taking the joint carbon or carbon atoms that are continuous. Now, I could decide to go this way. But if I go this way, I'll end here, which is shorter. So I take a longer route. That's what to do. You follow the longer route. If you follow the longer route, just keep following it. Single carbon atoms. Keep following it till you grab all of them. And then here. And then here. Notice that I left this guy still outside. So that's that basically. If we are to name this compound, we have gotten the parent chain. Let's now allocate locants. This is going to be 1. Now I'm going to start from this end because there's an attachment or substituent closer to this end than from here. You guys, so this is 1, this 2, this 3. Notice it is only the carbon in the circle that I'm allocating number, and I'm following it sequentially. 2, 3, this is 4, this is going to be 5, this is 6, this is 7, down 8, up 9, down 10, 11, 12, and then this is 13 basically. Now, haven't gotten this, it means that my parent chain is going to be tridecane. Now, what are the substituents? I have one substituent here, another substituent here, and then this whole bunch. Remember that this is methyl, it's just one carbon, while 3 carbon atoms is propyl. So my 2 substituents are methyl and propyl. This is already in an alphabetical order, right? A, B, C, D, E, F, G, A. Sorry, what am I doing? Yes, so it should be M before P. So let's continue. So let's name this. This is methyl, this is methyl. So this is going to be, methyl is on number 2. The other methyl is on number 3. So this is going to be 2, 3 dimethyl. Then I go to the next one, which is, where's the propyl located? This whole propyl is attached to carbon number 5. So 5 propyl tridecane. Now I'm giving you guys complicated structures basically to help you test your strength of understanding this, but it's quite simple. So hope this is clear. Yeah, heptadecane, yeah, that's for the older name, but for what we are doing now, hope this is clear. Hope it's clear. Oh. If you have any question, this is your time to ask. Oh yeah. Oh. Oh yeah. Oh. Kachi, praise. Oh, makes sense. Now, with that said, I'll give you guys an example to try. Just to help you guys learn this the more. Okay. So imagine you have okay. Okay. So try naming this structure, basically. Try naming this structure, basically. Now please note to have this in mind. Hope you know that this end that is attached to another element, there is no carbon in this place. Here you don't have a carbon atom because already OH is there now. So it's if it is like here or free, then you will know that there's a carbon atom there. But once it is attached to an element, there is no carbon atom there. Okay, the next, this A, so you name A. Then for B, the next structure you're going to try naming is this one. Let's see, let's add a little bit of spice to the name. Okay, then you guys try this one. Oh yeah, oh. Let's see. It looks confusing, but just follow that principle, and then with your understanding of what we did yesterday about naming, this should actually be very easy. Okay, so I'm going to give you guys like 2 minutes. 2 minutes to just try to answer that question. Yeah, I use it now. Okay. It's in more, okay. Okay. I see. Makes sense. Let's see. Let's try to put that together. Okay, what do you think is B? I'm going to answer everything together. Now, my advice is forget about the auto and the meta. Just leave the system. Use the normal numbering first of all. I told you that there is no number for number 5 and there's no letter term or number 5. You get? So put that correction, then we'll check it out together basically. Okay, so having said that, let's put one or two together and see which one of them is correct. Okay, back to the board. Now for this guy, now first of all, we already know this is phenol, which means we are counting number 1. Now our numbering is either going to be clockwise or anti-clockwise, and obviously we can see that if we count anti-clockwise, we'll have 1, 2, 3 before a substituent, but from here is 1, 2 and a substituent. So this is 1, 2, 3, 4, 5, 6. Naming this guy, this is carbon, carbon. This is carbon, 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 carbon. Remember, this is the substituent here, and this is also the substituent here. So let's get to work. The implication is that the name of this compound is going to be, we have 2, ethyl and butyl. Butyl, but butyl should come first, so we're going to name butyl first. Butyl is on number 5, so that's going to be 5 butyl, 2 ethyl phenol. So that's for A. So let's see, did any one of you guys, you could actually call this or 5 butyl O ethyl, that is auto phenol. Okay, so did any one of you get it? Praise. B they come first now. Normal. If you look at the alphabetical order, B comes before E. So praise. Yeah, the both of you made that same mistake, Seth. You forgot the alphabetical order. So but hope is clear now. You get the point. Hope is clear. Hope is clear. You suppose write like in the follow alphabetical order. Hope is clear, or just need your answer. Hope is clear. So always note that you are supposed to arrange alphabetically when you are naming. The substituents are arranged alphabetically. It's alright. So let's try the other one and see who got that. Now for the other one, we'll put our carbon first. 1, 2, 3, 4, 5, 6, 7, 8. It's an adjunction with this. You get, so carbon, then end carbon. Now yesterday in our naming, we said that if you have a functional group or a carbon chain of carbon atoms where there are many functional groups, make sure that your parent name contains all the functional groups. Which means even if you have a longer chain, but that longer chain does not contain all the functional groups, automatically just take the one that has all the functional. Like if we are counted 1, 2, 3, 4, 5, 6, 7, 8, you will notice that connection was lost. I hope the connection is back. Yeah, connection was lost for a while, but hope is back. Please respond. Please respond if the connection is back. Just say it's back so I'll know if I have to start resolving that. Okay, for want of time, I think. Oh yeah, I think it's back. Okay, so let's move ahead. Now, with that said, if you had looked at our study yesterday, that's why I told you guys to look it up before today's class. You will notice that we must include this OH, which means our parent chain will now be this. Now me they create all this confusing one just to test your strength in this. Okay, so with this is now clear. If we allocate our locants, it's now going to be 1, 2, 3, 4, 5, 6, 7. Now note that this is an alcohol. Now you are seeing OH. The highest functional group here is OH, so this is an alcohol. So this is now going to be heptanol. Now however, the OH is on the second one, so the parent's name is going to be hold on, it's not going to be heptanol. We've gotten that is 7 carbon, which is hept, but you are noticing that there is a double bond between 4 and 5. So this is going to be hept 4 in all. However, OH is on number 2, so this is going to be hept 4 in 2 all. So the implication is that the parent name, let's create the parent name. What we have as the parent name is hept because there are 7 carbon atoms. Now there's a double bond, so you need to indicate it. It is between 4 and 5, so you take the lower number, hept 4 in. But we don't end it with the E because we have to make sure it's an all. Now, where is the all located? It's located on number 2, so hept 4 in 2 all. And that's the name of the parent name. But we're not done. We have another substituent here. You remember, this hydroxyl is not a substituent. It's actually part of the name. If there were other functional groups, that's when you refer to it as a substituent. Now, in this case, this is propyl. So this is going to be 3-propyl hept 4 in 2 all. Was anybody able to get it? Let's see. Okay, I have, yeah, it's not the first one now. You see, you get the points now. So I hope the correction has been taken. Nice attempt from Anyaku. Yeah, from Kachi. Nice attempt. Yeah. So probably you omitted one of the carbon atoms, but hope this is clear. Okay. Yeah, so that's how it works. And praise, you were not in class yesterday, so probably it might be a little confusing for now. But the study is there. You can go and look through yesterday's study, and then it will be clearer. Just understand the general principle behind this thing, basically. Okay, so finally on structures, we are done with the different types of structures. But the final thing we need to understand about structure is when you are given a name, how do you convert that name to a structure? That's what we are going to be considering now. How do we convert names to structure? And I'm going to be putting out some basic principles. Once we look them through, we're going to just take that. With our understanding of these things, it's going to be easier to grab them. It's quite simple, basically. So we'll look at let me try to reduce the size so that I can be writing as so let me reduce the size a little bit and see. So I'll use one side of the board while in my analysis. Okay, yeah. So just to ask, hope we still see the write-up, the note. Hope we can still see the note. Hope the note is still clear. It's clear from my own end. I don't know about you. I want to reduce it a little bit. Okay, let me reduce it a little bit more so I can have like larger space. I think you guys can still see it, yeah. Yeah, I think you guys can still see it basically. So let me check. Yeah, I think it's still visible. It's, yeah. I hope you guys can still see it though, because I'm moving ahead. I can see it from my own end. I don't know about you. I think if you're using a system or a laptop, this should be okay. All right, let's continue. Now, let's consider these principles basically. Now, if you consider the first rule in I think the first part, let me bring this down. Oh yeah, calm down. So it should be there. So let's consider the first rule. The first rule says identify and outline the number of carbon atoms in the parent chain. So what I'm going to do is I'm going to write the name of a compound, and we are going to convert that compound name to a structure. So the name I'm going to deal with now is 2,2 dichloro hept 3 hept 3 in hept 3 in hept 3 in 3 all. Okay, so what we're going to do is we're going to convert this particular guy into a structure using the rules that we outlined basically. So let's go to the rules. The first rule says identify and outline the number of carbon atoms in the parent chain. Now the parent chain, as we can see, is hept 3 in 3 all. Basically that's the parent chain, and hept indicates 7, so we're going to put out that 7 carbon atoms. 1 2 3 4 5 6 7, and that's done basically. So that's the first thing you need to do. Make sure you outline the number of carbon atoms, and basically that's the first thing. Then we go to the next rule. The next rule says allocate locants to the carbon atoms outlined. So just give your numbers: 1 2 3 4 5 6 7. That's that basically. Then the next one says identify the functional groups present and attach them to the carbon atoms of corresponding locants. Now we have two major functional groups here. We have alkene and we have alkanol. So what we're going to do is just to simply attach it. Now we have all, which is the major functional group, and the alkanol is located on number 3 carbon. So which means you're just going to put OH here, and you have that basically in the attachment. Then we go to the next principle. The next principle says identify the multiple bonds if present and attach them between the carbon atom of the locant indicated and the adjacent carbon atom of higher locant. What does that mean? It simply means that because we have 3 in, which is for double bond, it is going to be between carbon number 3 and the carbon atom of higher locant, which means carbon number 3 and carbon number 4. So that's where we're going to put our double bond, and that's that. And this is what we have. So we go to the next rule, which is rule number 5. Attach other substituents to carbon atoms of corresponding locants. Okay, the substituents are the ones that are before the name. So which means we have 2,2-dichloro, which means chlorine will be here, and now chlorine will be here. So 2,2, chlorine, that's that basically. And dichloro. Having said that, we go to the final rule. What is the final rule? Fill the remaining spaces around carbon with hydrogen atom. Note, carbon can only form 4 bonds. So let's do that now. Now, if you come back here, this carbon atom only has 1 bond, which means the space around it will be 3. It's basic. Each carbon atom forms 4 bonds. So this is 1. The remaining spaces is 3. So 1, 2, 3 for hydrogen, basically. Then we come here. This carbon atom has 1, 2, 3, and 4 bonds. So it's filled up. We go to the next one. This carbon atom has 1, 2, 3, and 4 bonds. So that means this carbon is filled up. So let's check this one. This carbon has 1, 2, 3 bonds, which means it remains 1. So we fill it with hydrogen. Then we come here, we have 1, 2 bonds, meaning that there will be 2 hydrogen atoms. Then 1, 2, there will be 2 hydrogen atoms. Then 1, which means there will be 3 hydrogen atoms here. And that is the structure of 2,2-dichloro hept 3 in 3 all, basically. Any questions? Any questions? These things are not looking real, but if you follow the guide exactly as it's stated, I think it's quite easy to understand, though. You get. Any questions? Okay, no questions. Quite from Kachi. Praise, are you in class? Abi sleep don't carry you, they go. Okay, let's continue. Now, let's see. Let's try out this one. You guys should try this. Try converting this. How are you even going to do it, sir? If you write it, snap it and send it to the group. I will check it out in the group, because you can't send pictures here, or can you? I don't think you can send pictures to this, but just try. Y'all should do this now. Convert this particular. I'm about to write something. Okay, let's have let's have it. Okay, so let's say you have let's say you have 1 1 1 try. Let me make, so yes, oh no. So imagine you have 1 1 1 tribromo 4-ethyl 4-propyl dodec 2-ine dodec 2-ine no, dodec 2-ine 5-ol. Okay, so let's name this. So I said 1,1,1 tribromo 4-ethyl 4-propyl dodec 2-ine 5-ol. I presume you guys can still see this. Let me see. Okay. Oh yeah, my screen. Let me readjust my screen. The board be like say it commotes. Where did this thing do? Okay, so I think it's visible now. So let's try. Try and send it to the group. Try, you snap whatever you wrote and send it to the group. Okay. If you have, just say you sent it. If you sent it, just type sent and then I'll look it up basically. Okay, make una dey do o. Time e no dey again. Oya o, muna try. So try send it to the group basically. So this is basically the end of our study of organic structures. If there are any other thing, oh, there's one more thing though. I'll just highlight it and then we get into isomerism. We will still fit do isomerism today. Muna do o, time no dey. Okay. Muna do o, time no dey. 1,1,1 tribromo 4-ethyl 4-propyl dodec 2-ine 5-ol. If you do that, send the picture to the group, then I'll look it up. Once you're done with it, just send it to the group, then we'll now do the correction quickly. good. Okay. Okay. So yes, one of you have sent, and yeah, I think it's correct. Let's now do that together. Let's do that together. Oh yeah, back to the board. Wait, did I put on the audio? Yeah, it's on. Okay, so back to the board. Let's put this together and convert this structure into a name. Now, remember the first rule says identify the number of carbon atoms in the parent chain, and it's dodec. Dodec is 12, so we're going to put out 12 carbon atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then you allocate locants. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Once you're done with that, the next thing to do is to look out for the functional group and allocate it. This is all, which is hydroxyl, and is on number 5. So put that here, OH, and you have that. Then we go to the multiple bond, 2-ine. Ine is for triple bond, and it is between 2 and 3, so triple bond, that's that. And having done that, we now attach our substituents. We have bromo first. Bromo is on number 1, 1, 1, 1. Tribromo, we're done with that. Ethyl is on number 4, and ethyl is C2H5. And then also have number 4, propyl. Propyl is C3H7, and that's that. The remaining is to add hydrogen. There is no hydrogen here. 1, 2, 3. This is 1, 2, 3, 4. So it's filled up. This is 1, 2, 3, 4. It's filled up. This is 1, 2, 3, 4. Filled up. This is 1, 2, 3. Remaining 1 spot for hydrogen. So we put that. This is 1, 2. Remaining 2 spots for hydrogen, H2. 1, 2, 2 spots for hydrogen, H2. 1, 2, 2 spots for hydrogen, H here and H here. 1, 2, 2 spots, H here and H here. 1, 2, 2 spots, H here and H here. 1, 2, 2 spots, 1, 2. Then there's just 1, which means there will be 3 hydrogen atoms remaining, which is CH3. If you have this as your structure, then you are correct. Okay, so that's that basically. Dubem, you came late to class. We are dealing with organic structures, IUPAC nomenclature, organic structures, basically. That's where we are. Okay, I guess this is understood. That's besides Dubem, you came late, so probably you might not have been following. But just day class, we will talk 1 or 2, just they grab. Yeah, as for the rest of you, hope it's clear. Hope no confusion. Oh yeah, Muna talk, time no day. Because I am probably gonna introduce the concept of isomerism today. Even if we don't finish it, we'll try, shall we? If we finish up. Oh yeah, are we done? No confusions. Okay, let's continue. Now, having discussed this, the next thing we are going to talk about, which should be the last thing for today, is isomerism. We may or may not finish the study, but at least let's start. Let's introduce it. Now, I'm going to put out. Okay, I'll put out some examples or things that we are going to try out. We are going to try out later on. Okay, sorry about that. I had to resolve something, but we still do class. Yeah, so back to what I was saying. I will put out some examples later for us to go through and then try them on our own. Probably I'll put that out in the group. You get, but let me just put it out here so you guys could see what I mean. Name to structure. Okay. So these are some of the examples you guys can try on your own later. I'll still send this out to the group, but you could, if you notice, these ones are actually quite simple. You get, they are very, very basic and simple. Oh yes, I did not talk about the cyclo group. Let me just quickly, once you hear cyclo, the implication, let's name, we're going to do number, let's do number 3. We're going to do number 3 and number 3. Basically, I'll do number 3, then you guys are going to do number 8. I'll do number 3 and you do number 8, basically. So let's do that. I'll do number 3 just to show you the cycle before I get into isomerism. And then you do number 8. Number 3 is 1,4-dimethyl cyclohexane. 1,4-dimethyl cyclohexane. I'm going to have to take it out so that I'll have, or reduce it. Okay, let me just reduce it. Let me just reduce it. But it goes small, where? Where's my mouse? Sorry, guys. Okay, so let me just reduce it. Where do you reduce? Okay. Okay, sorry, yeah, let me just reduce it so that we'll have space on the board. Okay, so yeah, back to you guys. Okay, now, having said that, I said I'll name number 3. I think it's still clear, right? It's still clear. I'll name number 3 and you guys are going to name number 8, basically. Let's do that. Now, whenever you have a scenario where, for instance, you have a cyclo. Let's look at the name of number 3, for instance. Number 3 is 1,4-dimethyl cyclohexane. You will notice that in this case, the parent name is cyclohexane because that's the last part. Usually, the last part of an organic name shows the parent's name. Cyclo means circular form, which means you are going to put your hexane such that it will be closed. 1, 2, 3, 4, 5, 6. Then you close it up. This is going to be in a hexagonal structure, basically. If it was cyclopentane, it will be 1, 2, 3, 4, 5. If I close it up, basically. If it is butane, 1, 2, 3, 4. This is cyclo. Cyclo means make sure there is no open end. Just put it in a cycle. I presume this is clear. Is this clear? Hope it's clear what I just did. Hope it's clear. Yes, just one response and then I continue. Hope it is understood. Yes, what I just said, hope is clear. Mona talk, no deal. Yeah. Just one response. I just want one response and okay, very good. So when you hear cyclo, it means that it is going to be in a cycle or a circular form. The chain will close. That's basically the point. So when they say cyclohexane, let's come back to my board. The question says 1,4-dimethyl cyclohexane. So the implication is that our number, just give numbers 1, 2, 3, 4, 5, 6. Now, the methyl group, the name is 1,4, which means methyl will be on number 1. This is number 1. I put a methyl group. And then methyl will be on number 4. I put a methyl group. And that's that basically. This is 1,4-dimethyl cyclohexane. This is not a benzene ring Why? There is no circle in the center, and then there are no triple bonds. There are the double bonds. There are not 3 double bonds existing in this chain. So some of you might mistake this for hexene, but this is not hexene. This is not benzene. Sorry, this is just hexane, and this hexane now has 1,4 dimethyl hexane, and that's that basically. Okay, I hope this is clear. Is this understood? Do I need to try one more? Do I need to show you guys one more? Do I need to show one more? Okay, do I need to show one more example? If it's necessary, just indicate. Sure, na still dey class new. Abi una don go sleep? Okay, one more example. Okay, I'm going to do that. Okay, one more example. I will not use this one on the screen. I want you guys to do that yourselves. You guys do that yourselves. Okay, well let me try putting down some names of some compounds. Yeah. Okay, so let me try. Okay, so let's see. Let's take all these guys out. Imagine the name of the compound is 1, 2 dichlorocyclohexene. So the parent chain in this case is cyclohexene, which means 6 carbon atoms in cycle. 1 is here, 2, 3, 4, 5, and 6. So I just link them up. So that's the cyclohex first. Then it's ene. Please, once you see that there is no number between the infix and the suffix, the implication is that it's on number 1. So ene, which means that is a double bond between number 1 and number 2. Anybody can be number 1, anybody can be number 2. So we call this one number 1. So that's where the ene is located. Now they said 1, 2 dichloro. So let's fill that. We are done with the cyclohexene. That's this part. Then we allocate locants. Number 1. Let's use different colors. Number 1. Now remember, we are going to have to count from this side because the double bond is already on this side. So 1, 2, 3, 4, 5, 6. So with that, they said 1, 2 dichloro, which means chlorine is on number 1 and chlorine is on number 2. Now, and after that, we now fill with hydrogens for the remaining spaces. This is carbon, 1, 2, 3, 4 bonds. So it's filled up. This is carbon, 1, 2, 3, 1, 2, 3, 4. There are 2 bonds here. So this is 1, 2, 3, 4 bonds filled up. This is carbon. This is 1, 2. Then the remaining is 3, 4 for hydrogen, basically. Then we go to the next carbon. This is 1, 2, 3, 4. This is 1, 2, 3, 4. This is 1, 2, 3. Okay, I presume the connection is restored. Okay, should we reschedule the class after this? Should we reschedule the class after this? After this example. Yeah, so just what's your answer? Let's probably will reschedule the class after this example, but let's finish this at least. Now, back to what I was saying. So if we are to consider this, this is going to be 1, 2, 3, 4, 5, 6. This is 6 carbon atoms, and hexene, given the number 1, 2, 3, 4, 5, 6. The hex in means that it's between 1 and 2. Once there is no number, it means that the locant of the double bond is number 1. So that's between 1 and 2. Now let's fill up the rest. They said it's 1, 2 dichloro. We have 1 chlorine here, another chlorine here. Then hydrogen, this is 1, 2, so just 2 hydrogen atoms. This is 1, 2, so 2 hydrogen atoms. This is 1, 2, so 2 hydrogen atoms. This is 1, 2, so 2 hydrogen atoms. And that's that basically. We'll refer to this as 1, 2 dichlorocyclohexene. I presume this has been helpful. We don't try. Let's reschedule the class to another time and finish up isomerism and get into the others. Now, the remaining part of the study just has to do with reactions. You might say yes, lab preparation. Lab preparations are reactions. So, with your understanding of this concept, if we get to study reactions or the other parts of the CHEM122, the only things we need to look out for are the different reactions that are involved. Thank you very much for having this class with me. See you guys.